So now we are live. So we're going to start. Thank you everybody for coming. And as always, we're going to begin with a little bit of what happened this week according to science. And then we're going to give a little introduction to our today's opponent. So let's see. What happened today and the rest of the week? So we have interesting things that happened this week. First of all, Watson Crick and Rosalind Franklin published the structure of DNA. That's a really, really important date, happened this week, in 1953. Then we have on the 26th, yesterday, we have the biochemistry, the Spanish biochemistry, Margarita Salas, that made this didactic museum that has her name. Then in today's day, we have Sheng Tianhui in 1923. She was born and she was like analysis in mines and about the fabrication of silicon. So really important for today's technology. And a day like tomorrow, the physicist Hertha Houghton. She was working with electrical arcs and waves in sand and water. Then the 29th, we have this robot, humanoid robot that goes under sea called Ocean One. Then we have another important one. The physicist J.J. Thomson discovers the electron. And finally, one of my favorites is that we have on the 1st May, we have Joachim Tycho and Albert Levan, that they discovered that we have 48 chromosomes, the humans. So really interesting thing. Now, let's mute yourself. And there you go. So now we're going to, oh my, what did I do? Okay. So let me introduce you to Dr. Seyed Sohail Masuri. He's an associate professor in the Department of Chemical and Biochemistry Engineering at the Technical University of Denmark, an affiliate faculty at Sino-Danish Center of Education and Research in Beijing, China. He received his PhD in 2016 and the MSc in 2013 in Chemical and Biochemical Engineering, both from DTU. His current research is focused on the process systems engineering, system dynamics, EdTech focus on computational agility, AI and quantum computing, socioeconomic technological analysis of complex dynamic systems, process synthesis, design, control, and intensification with the focus of chemical, pharmaceutical, and biomanufacturing sectors. He is a senior member of the American Institute of Chemical Engineers and a Danish delegate to computer-aided process engineering, working party of European Federation of Chemical Engineers. He is also a treasurer and board member of the European Committee for the Use of Computers in Chemical Engineering Education. So without further ado, let's give a great welcome to Dr. Seyed and his talk. Dr. Seyed, you are muted.
Thank you very much, Raquel, for a very nice introduction. So I will start my talk. So I'm an associate professor at the Technical University of Denmark, and this DTU's mission is to develop and create value through the technical and natural sciences for the benefit of the society. And the university was founded close to 2 centuries ago by Hans Christian Ørsted, the one who discovered electromagnetism. So a couple of years ago, we celebrated the 200th anniversary of Hans Christian Ørsted's discovery of electromagnetism. And if you look at DTU, founded in 1829, it has evolved through the time in several defining moments. And today, DTU is the flagship technical university in Northern Europe with the motto of technology for people. And our research is going to provide education, innovation, and scientific advice. So DTU is located on the northern suburbs of Copenhagen in the city of Ljungby. And it has a number of campuses and research facilities across the country as well as in Greenland. So where did I come from? So Denmark. Denmark is this tiny country of 5.5 million people in the Northern Europe, in Scandinavia. Here is Copenhagen. Here is Ljungby on the northern suburbs of Copenhagen. And as you can see, this is the Little Mermaid of Copenhagen that we are very proud of. This is the DTU Central Administration Building. And this is the Nyhavn, one of the scenic places in Copenhagen. So with this brief introduction, I'm going to start with my talk on emerging trends for sustainable bioprocess developments. And I will emphasize on the application of artificial intelligence, quantum computing, and beyond, and how we put them into the perspective for chemical and biological process development. So where is the motivation and challenge? Well, this is not a secret. Our world is facing a number of challenges today with respect to the water, energy, food, and waste. So the economics are always important. So it is always a desire to improve the economics, to reduce the poverty, to create jobs, to increase value for the society by decreasing the capital expenses as well as operational expenses. Why we want to have chemical and biological processes that are more resource efficient. And finally, we want to move along the lines of the definition of sustainability, which is to safeguard the interests of future generations by responsibly using the current resources. So we need to improve the way that we do our manufacturing. We produce our products, and commodities, and the specialty product. And the question is, how do we achieve these improvements, and how can they be attained? That is through generating innovative solutions to obtain more sustainable designs. I'm a chemical engineer by training, and my area of research is process systems engineering. So process systems engineering is an interdisciplinary field within chemical engineering that its objective is looking at the complexity of different systems through development of systematic procedures based on mathematical models and computational techniques. So as it was defined by Roger Sargent, who founded the discipline of process systems engineering, process systems engineering is all about the development of systematic techniques for process modeling, design, and control, and so on. And these are some of the applications of process systems engineering within modeling of properties, products, processes, and developing computer-aided tools. Product synthesis, design, and analysis, looking at single molecules, mixture, and blends, process synthesis, design, analysis, separation processes, process intensification, and finally integration towards achieving more sustainable processes. So in order to do this, we need databases, we need model libraries, we need methods, and we need computer-aided tools. So if you look at how we systematically develop a process, the first step is process synthesis, where I'm depicting here in this blue schematic. So in the synthesis stage, the objective is to generate multiple processing routes. So in order to go from a single raw material to a final product, there are various ways that it can be produced and through various processing routes. The question is, what is the best processing route that can fulfill an economic and or an environmental objective function sustainability simultaneously? And today, we are all aware that it is not just the economics that has to be maximized, it is also the environmental impact. So the design and analysis is where we obtain the processes, the optimal processing route. We do the rigorous design, and while we do that, we can identify the process hotspots and tackle them through process intensification. And finally, in order to guarantee the implementation and safe operation of the processes, one needs to think of the control of this process. So for this, we need databases on compounds, properties, experimental data. We need model libraries, we need methods, and we need computer-aided tools. So the problem is often formulated in mathematical form. So as you can see, there is an objective function for the task to be maximized or minimized. We need to have process models. These are subject to a set of constraints. For example, equality constraints or inequality constraints, and each of one of these steps and formulations requires different classes of problem formulations and solution strategies. So now what I'm basing my talk on is on this multi-layered view of chemical and biochemical engineering to show how we can go from the inner core interface of chemical engineering, where fundamentals are located, to the middle interface layer and outer interface layer, with the overall objective of fulfilling the societal needs through educating the needed engineers who can apply their knowledge in the industry. So inner core fundamental layer for processes and products is to achieve the knowledge that is required for different aspects of chemical and biological process development. For example, transport phenomena, unit operations, process integration, control, and many more. And there are adjacent areas such as organic chemistry, analytical sciences, and many more. So our process systems have a multi-scale nature. And the multi-scale nature of process systems signifies that we start off from the molecular and atomic level interactions all the way to enterprise-wide and societal level. These are all connected. They're not disjoint from each other. So often, a pain is felt, for example, in the society with a product at enterprise-wide level or at a different scale of operation through a product manufacturing and life cycle. However, the root cause for this pain may well lie somewhere else in another scale. So having this multi-scale understanding of the process systems is essential to tackle some of the most challenging problems that we are facing today. These are some examples. For example, this is one example on modeling stone wool dissolution. The idea here is to provide this company Rockwool with a model that is able to predict dissolution rate to reduce health impacts in human lungs. How can we basically understand that? We need to go all the way to the molecular level and find a better structure for the dissolution of these molecules. Then later on, that structure is gonna be something that will be realized in form of the bulk product. Another example is modeling of liquid-liquid phase transfer catalysis. In this case, this is not necessarily a biological example. uh, but as you can see, the idea here is that we integrate computational chemistry with multi-scale modeling to provide a domain to explore new solvent catalysts and reactions. So what we're doing here when we're talking about process intensification in these type of reactions is that we want to combine both the reaction and separation, and we have applied it to the case of hydrogen sulfide valorization to convert it to valuable products. This is also another example for fish diagrams as a tool for emulsion design. Designing emulsions is very, very crucial in formulated product in formulated products. And today, a lot of formulations are made by trial and error. However, the idea is that if we can go towards the direction to save enormous amounts of time for formulation experiments and to do them through computer-aided approaches. So we have a wide range of formulated products, from pharmaceuticals to cosmetics to detergents, etc. However, the idea here is that we can go in that direction by understanding the molecular scale interactions. We can come up with better formulations at lower cost. So this is another example that then how we use these fish diagrams. This is a formulation. Then we combine it with image processing, and we integrate the molecular scale modeling with artificial intelligence to provide an integrated causal effect tool for designing emulsions. Another example at the fundamental layer is micellar catalysis, again in organic synthesis, in synthesis of many pharmaceutical products. Solvents are being used at large. However, micelles are water-soluble structures that are more sustainable, that are green, and they can well replace solvents. The question and challenge here is that how can we then utilize these micelles and perform the organic synthesis reactions inside the micelles instead of doing them with the organic solvents. Now moving to the middle interface layer where science and engineering meet each other, the idea is that innovative solutions for service provisions need to be determined. And this requires additional knowledge in terms of the integration of science and engineering, leading to the development of innovative solution approaches to process integration and intensification, as well as ways to manage supply chains and monitor economic, ecological, and societal impacts. That is where data science and machine learning may come into the picture. So one thing that we need to know is that when we talk about data science and machine learning, it doesn't mean that everything that we are solving now and we are getting the result, we have to repeat solving the same thing with machine learning approaches. The idea is that how do we leverage the great amount of prior knowledge in order to complement the knowledge that we have already acquired through the understanding of the physics, chemistry, and biology. So I'm here quoting Venkata Subramanian from Columbia University, that he says, mechanism-based causal explanations are at the foundations of science and engineering. So what we are developing in my group are hybrid machine learning modeling frameworks, mainly for particle processes. And these particle processes can range from anything from fermentations agglomeration processes, crystallization, precipitation, and so on. So the idea of the hybrid modeling structure is to combine the machine learning model with the first principle models. So as you can see, we do embed the first principle model or mechanistic model within the hidden layers of the artificial neural networks, and in this way, we can overcome the risk of overfeeding or underfeeding that is quite common with pure data-driven approaches by constraining the predictions and the estimation of the parameters of the machine learning model to bring them closer to the reality. Because otherwise, since machine learning models, they do not have an understanding of the laws of physics and chemistry, they may very well drift away from a reality, and they may not have a very good predictive ability. So one thing that we need to know and also note is that chemical engineering problems and biological engineering problems are different from image processing or voice recognition problems. Often in the industry, we don't have this vast amount of data that, for example, the companies like Facebook and Google and so on are collecting. We rely on sensors, we rely on certain operating conditions, and the amount of data that we have is different. So we need to acknowledge that we need to combine the machine learning approaches with the mechanistic understanding that we already have from the physics, chemistry, and biology, and we need to continue expanding our understanding of the fundamentals. So what we have done here, we have implemented this framework using a population balance model as the mechanistic model, and this is the first example where we have looked at the pharmaceutical crystallization process. As you can see, there are 5 different batches that they started all at quite different starting conditions, and we use this online image-based particle size distribution analyzer, which is a flow cell-based technology, to obtain the data. So the sensor and the data that we acquired apart from the process data that we were obtaining, including temperature, pH, and conductivity, were images. And as you can see, we acquired the raw images, and then we have used the segmentation algorithms to process these images, and then analyze the particles, and then build the hybrid model. And we can see, in spite of the quite different batch starting conditions, we managed to make quite good predictions. Another example is looking at agglomeration processes, where same sensor was used, but here, because of the complexity of the agglomeration process, we used the density functional theory, and we modeled from first principles the interfacial and tension effects between the particles, and now we have embedded these calculations within the neural network structure, and we have been able to show that we can go to a level of complexity that was otherwise not possible in the past. So where do we lead with this? To digital twins. So digital twins are cyber-physical units which have the ability of interacting and optimizing a process real time based on the measurement data, model training, and control actuation. And as you can see, this is a bioreactor. This is the image processing sensor, and then it takes the information, and then it optimizes the process. So when we are talking about digital twins, it is not something that we are reinventing the wheel. It is a lot of the fact that at the same time that we are developing our modeling competencies and strategies in modeling more complex processes using more advanced measurement technologies, we are also taking advantage of the more availability of computational power today to do and implement some of the concepts that were not possible for implementation some years ago. Now, looking at the outer unifying layer, which is dealing with the improved social benefits, and that is to achieve a larger vision of the true needs of the society with respect to limited availability of the resources. And when it comes to chemical and biochemical engineering, the integration of the know-how with other disciplines like sociology, ethics, political science, and with many other domains of the society is becoming important. That is where we can look into concepts like such as circular economy and resource recovery when looking at the chemical and biological processes. So if you look at the production cycle, so we use the raw material, we produce the products, we consume the products, we generate waste, and this is the part of the circle that needs to be closed in order to bring back the generated waste back to the production cycle. One thing that we all need, in my view, to take into account is the circular as a circular economy. Well, I can accept that it is a term that is being used quite widely these days. However, from a thermodynamic point of view, from the second law of thermodynamics, processes in this way cannot be really circular. I mean, we still need to spend energy to provide circularity, as well as the fact that we are degrading the resources after all. So one thing that we need to also be mindful, and that is where the other dimensions of the society come into play, is that it is not only the technology that will solve our some of our problems that we are facing today. It is also our own human behavior. We need to also be mindful of better ways of consumption more responsibly at the societal level as well. So this is one example on the process synthesis design and analysis for biosextinic acid production. As some of you may know, succinic acid is an important chemical building block with a lot of applications across various sectors. There are efforts in the past years to produce succinic acid through biological pathways. And what we have done in this study is that there were 4 plants, biosuccinic acid plants, that were built in the last decade. However, today, those plants either have gone bankrupt or are struggling economically. So we started looking into the reasons behind this issue. So what we did was that we collected all technologies at all different processing stages, looking at the 3 generations of feedstock: first generation biomass, second generation biomass, and third generation biomass, different pre-treatment technologies, fermentations, host organisms, and so on, all the way to the product. So we created this superstructure of alternatives. When we talk about superstructure, it means that we included all and evaluated all logical and feasible processing pathways to produce biosuccinic acid, and this superstructure consists of more than 14,000 alternatives that were evaluated. So we did an optimization arrived into these four optimal process configurations in terms of economic profitability. I mean, the paper is published in Energy and Environmental Science. You can find it and read it. But one thing that was quite interesting in this analysis was that the plant capacity turned out to be one of the main issues, apart from the fact that the plants that were built were predominantly built, number one, based on the availability of feedstock, number two, based on the patents and IP protection that the investors had on a particular microorganism or approach. So that means that they did not go actually through this kind of optimization to find the most optimum pathway. Instead, they went towards the thing that they could economically protect. Plus, the capacity of the plants that had been built was suboptimal, meaning making them susceptible to the fluctuations in the oil prices, because succinic acid from fossil bases is competing with biosextinic acid. So when the oil prices go down, biosextinic acid plants, if they are not designed properly and the optimal processing route is not identified, they may well go bankrupt. And the other thing is that the capacity of these plants had to be was suboptimal, that it make them economically not robust. Another example is we looked at a zero waste production concept. That means to integrate the biodiesel production. You know, biodiesel production, one of the main wastes from biodiesel production is glycerol production. The more biodiesel is produced, the more glycerol is produced. But there is a market saturation for the for glycerol globally. So what happens here is that we said that, okay, we have done the optimization on the succinic acid. Glycerol is a good substrate for production of biosextinic acid. So we integrate biodiesel production with biosextinic acid production from glycerol, and we also assume that we build this plant, for example, near to a CO2 capture facility, that then we can produce methanol from CO2. So meaning that what we needed for this biodiesel production was only waste cooking oil, and then we get succinic acid and biodiesel out. So we use CO2 and waste cooking oil, and then we get biodiesel and succinic acid out. So now we want to see how did the performance of the scenarios take place. So we looked into actually 4 different scenarios where all of them were combined, or just 2 by 2 were combined. So what we came at the end is that full integration, so at the end of the day, was not the most optimum case. I mean, we cannot guarantee that our solution is a global optimal solution. However, we can conclude from this study that also when it comes to process integration, care must be taken not to integrate necessarily everything with everything. May not be more sustainable. So you need to, again, when it comes to process integration, find the right processes to integrate them with each other. And in this case, the most sustainable and economically viable case was to combine biodiesel production and succinic acid production, and giving up on the production of methanol from CO2. Now, if you want to look at more complex problems from a model-based approach, and then reduce the try and error, and we try to use this type of optimizations and modeling strategies, artificial intelligence, and so on, we need a more computational power. So does any of you remember floppy disks? Perhaps those of you who are born after the year 2000 may have actually never seen floppy disks. Some of you may have actually never seen a CD, right? So and today the memory sticks are also not being used as much. So if you also look at this monkey, that it was us, and we have evolved over thousands of years, but we can also see that the technology has also evolved a lot, and today we are on the notion of the cloud systems and cloud computation and all this kind of thing. So can anybody recognize this? Can anybody tell me? I mean, feel free to open your microphone and tell me, does anybody recognize what it is?
That's like the first computer.
The first computer, right?
Yeah, it is one of the first computers. It is the ENIAC computer, and as you can see, it was such a large computer at a few bytes of memory and capacity that it could do the computations. And today we are approaching the era of quantum computing. So we're the first idea of a quantum computer is often credited to Richard Feynman, but there were others that talked about quantum computations, but Feynman first time talked about simulating physics with computers in 1982. However, the first quantum computer came out in 1998 in a research lab, and we also had the first quantum algorithm developed in the 90s. So there's a difference between the quantum logic and the classical bit. So this is the classical bit of 0 and 1. However, this is a qubit. So a qubit is working on based on the superposition of an electron or orbiting around it. So n qubit system can be in superposition of all of those states to the power of n states at a given time. And it needs the value of coefficients of all of the 2 to the power of n states basis to be fully recognized, meaning that one qubit has 2 to the power of n bits and more capacity to store information than a classical bit, right? But if you look at the current status of quantum computing, the first commercial quantum computer was introduced to the market by IBM in 2016. And from the first quantum computer that was the research one, very noisy quantum computer that was 2 qubit, today IBM has reached over 200 qubits, and their ambition is to get into logical qubits of 1,000 qubits that they can scale them by 2024 or 2025, just in a matter of a few years. So, but when we look at the application of quantum computers and chemical and biological engineering, I mean, there's plenty of opportunities. And this is also the demographic distribution of the current research around quantum computing. As you can see, USA is by far the front runner in this. So why should we use quantum computing? Quantum computing can fundamentally change what is computable, because there exists plenty of problems that are called NP-hard problems, or non-polynomial problems that are highly entangled, and they're not impossible to solve on a classic computer, but they're infeasible to solve on classic computers. And quantum computing can provide the means to scale the computation complexity. Such examples on designing enzymes, designing the transition and metals, molecular conformation, problems that could have relevance to chemical and biological engineers. And it also has insights in classical computing because many classical algorithms are quantum inspired in chemistry and physics. And it also challenges classical algorithms to compete with quantum algorithms. So this is again a landscape of the available quantum technologies. So we have gate-based technologies, we have topological technologies that Microsoft is improving in developing gate-based technologies, which are the Google, IBM, Rigetti, and quantum annealing. So there are different type of hardware, and there is a race at the moment on developing different type of hardware based on different material and different physics, quantum computers will not be similar to the general purpose computers that we have today. It's just like that 100 years ago, if I wanted to go from Denmark to Mexico, I had to sail with a ship over the Atlantic, which would have taken me a lot of time and perhaps a lot of dangers for not ever making it to Mexico. So today, if I still want to go to Mexico, I need to get out of my door. I need to use my legs to walk on foot to the bus stop, take the bus, then go to the airport. So the major step is actually the jumbo jet that takes me from Copenhagen airport to Mexico City airport in a matter of much less time and more safe, guaranteeing that I will reach the destination. So this is also what perhaps the quantum computers will do for us when it comes to computation in the next few years or decades. Just for you to get a little bit more insight, and the quantum computers are particularly advantageous in solving class of optimization problems called unconstrained quadratic optimization problems, and it is for the type of models that there is a high connection between the states in the model and is actually generic enough, this type of optimization problem, to encapsulate many problems. The quantum computing devices still lack the capacity to solve the breakthrough problems, but they are underway. However, we also need, as chemical and biological engineers, know that this kind of hardware is coming into the picture, and we need to be prepared by understanding them, by developing algorithms, and by finding the right problems to be able to use them to advance the chemical and biological development in terms of designing new catalysts, designing new drugs and enzymes, proteins, and so on. And one of the examples around quantum computing is property prediction. And the question is that where can quantum computing be useful? It may not be very useful if the goal is to calculate or capture major trends or producing semi-quantitative results. But it may be actually very useful looking at, for example, enzymes with a transition metal in the active site. That is because transition metals often require advanced approximate methods for treating electron correlation on a classical computer. So that is where the quantum computer can really help us do these calculations and advance the state of the art. So again, back to the micelle example that I gave you. I mean, one idea could be that we could, for example, design micelles by combining the quantum computer. So taking the part of the problem that requires a lot of effort or is simply infeasible on a classic computer to a quantum computer, and we solve the rest on a classic computer. This is also an example of looking at the molecular conformation a problem. So molecular conformation is the atomic arrangement of a given molecular configuration in three-dimensional space. And while the configuration specifies which atoms are connected to each other, so what we know usually in the textbooks about the atoms is their configuration, but they also have a conformation which specify the angles and lengths of the bonds between these atoms, and these lengths and bonds determine some of the major properties of a certain molecule. And this is an overall structure of hybrid quantum classical quantum computing algorithms can be launched on classic computers. So for this, we also need education for artificial intelligence, quantum computing, and a lot of emerging trends. We need education, the principles and the fundamental science. We need tools like sensors, like hardware, like many other things. We need the means of their implementation, and we also need to find the right context for their application in the society. And we also need to be agile and be open to adopt and develop pedagogical approaches. So another example for this, now bringing this entire thing together could be going more and more towards development of digital twins and cyber physical units. And finally, this is Calumbo. So Calumbo is one of the world's most sustainable and comprehensive industrial symbiosis, where they have moved in the past 50 years in Denmark towards the concept of process integration and waste minimization. And again, looking at larger symbiosis and the structures requires a lot of effort. So large symbiotic efforts are important. Today, we have the possibility to look into larger and more complex process systems. There's a need to develop education. At the same time, we develop technology, and the new modes of education need to be developed to meet the demands of the industry. And last but not least, we recently also organized a workshop in Denmark on the applications of quantum computing in chemical and biochemical engineering, which was the first of its kind in the world. And we are very much looking forward to collaborations, and anybody who would like to join us in doing experiments and doing some adventures in this field. So thank you very much.
Okay, thank you so much for the presenter, Professor. I don't know if I'm going to pronounce it correctly. Sorry. How do you pronounce your name?
Seyed Mansouri.
Seyed. Okay, thank you so much. Thank you so much for the presentation. I don't know if any of the attendees have any questions to the presenter. In the chat, I guess we don't have any questions. I don't see also I don't see also any questions here. There's some comments. It was a nice presentation, interesting presentation. Maybe I just have one first question. Okay. Okay.
Hello, Professor.
Hello.
Nice to see you. Well, amazing presentation. It's really nice and a huge impact in the research and the collaboration for the future. I think this strategy using modeling and the implementation of machine learning and quantum computing. It will be the focus for the companies, but from your perspective, as you are very linked to pharmaceutical industry, how important is for the companies now to implement this approach for the scaling up on the systems as a strategy for the future, no?
Well, thanks a lot, Roberto. I mean, to implement quantum computing, it may be a little bit early for enterprises to be able to realize their full potentials. But certainly, these technologies are advancing at an astronomical rate. We still don't know if we are going to have anything tangible within the next few years that can actually help us in solving one of those very real challenging problems. But we need to work, and we need to explore, and we need to try.
That's amazing. I just a little question is how we can work with the digital twins in the industry.
Well, digital twins are being adopted in the industry. So digital twins have the advantage of providing the means for process, for example, scale up, for process optimization, process control, and in general, providing the industry to move from a recipe-driven type of production to more a know-how type of production, by having the models of their system and keep improving them by using their plant data and having these cyber physical units to help them move towards more sustainable, more optimized production.
Thank you very much.
I need to apologize. I have a hard stop in 1 minute. As I need to go to another obligation. But I would like to thank all of you here for inviting me, and please do feel free to drop me a line or connect on LinkedIn, and we can definitely have more conversations along these lines.
Okay, excellent. Thank you so much, Professor. And yes, of course, we'll send you the certificate of your participation here today. And thank you so much to
Thank you very
all the
much.
attendants. Thank you.
And have a nice day. Bye.
Thank you
You
very
too.
much. Goodbye.
Bye.
Bye.
Ok, gracias a todos por su asistencia y nos vemos en 2 semanas para el siguiente.
Sale. Gracias, Mariana. Corre, corre.